No. For power applications, you don't want to use op amps. I mean, otherwise this op amp will have to process the full power, right? For power applications, you have to use a LC filter typically. We were, we typically that's what you would use to connect to the grid for a single phase converter. One of the each phase would be connected through either L or LC or LCL. There's a lot of papers about whether you should use or these are three variations. So you can have your converter here, here, or here. This is the simplest form is just a simple L filter. Another form is a LC filter. Another form is an LCL filter. Right? If you from 420, if you didn't take 420, or from 214, for example, you know that anytime you have a reactive element, an L or a C, then your circuit, if you're going to write your differential equation, you will have an additional variable. In electrical circuits, what are the differential equations? Why are the differential equations created? Anytime you have a capacitor or inductor, you have VL is equal to LdI by dt, right? Or IC is equal to CdVC by dt, right? So anytime you have an inductor or a capacitor, you will have which current? It's the capacitor current. Which capacitor? This one. Which inductor current? This inductor current, this specific one. So anytime you have an inductor or a capacitor, you will have a new variable that you are gonna differentiate or integrate. So it's your equation will go up one level. So if you have two components, two capacitive, one capacitor, one inductor, you have a second order equation. Three components, third order equation. Four components, fourth order equation, right? And then if you relate that to your signal processing course, right? When you were designing filters, you wanted to design a low pass filter. This was your corner or break frequency, right? And then or 3 dB frequency or whatever, right? Had many names. Corner, break, 3 dB frequency, has many names. And then from here, you're attenuating. So for example, this is gain of 1 dB. This is gain of, I don't know, 40 dB or whatever, some gain. Some gain corresponding to a certain magnitude in real numbers without dB. And then you're trying to attenuate everything else, right? So you're trying to attenuate the signal. This attenuation, let's say this is 50 hertz. Let's say this is corner frequency. So anything below 50 hertz, you were magnifying, right? Or just passing through with a gain of 1, depending on what this number here was, right? And then anything after that, you're attenuating. Are you attenuating it this fast, or this fast, or this fast? What does this depend on? Huh? The order of the filter. The order of the filter is defined by how many reactive elements you have in your circuit. That's if you're using a passive filter. If you use a op-amp filter, of course, it's a little bit different, but very similar still. I mean, I think it's still very similar because you still have these passive elements, these reactive elements. You have L's and C's around the op-amp, so it will also be defined by that. But passive filters, yes, this is defined by how many components you have around. So yeah, you'd never use a op-amp because then you have to pass all power through it. And op-amps are typically low power electronics, right? So you don't want to use this. You're in a grid connected converter, you'll use this, or this. Which one? It will depend on the harmonics that you have in your system and how fast filtering do you want to achieve, etc. The performance of the filter. But typically, most converters, I say most low cost, typical low voltage level converters would be just a pure L, grid connected ones. Okay? So now, for the half-wave rectifier chapter, I just want to go through the equation of the chapter. So I think we went to the waveforms quite a bit, right? So do you have any questions on waveforms? No questions? So I think I just want to go through the equations so that, because I will put the due date for the homework for this chapter today. I mean, I will just, it will be, next week, early next week. Yeah. So, for me to do that, I just wanted to make sure we're good on the equations as well. Okay, so for the half-wave rectifier with the resistive load, we went through the waveforms. Again, the objective of this was to what? Create AC, DC from AC. DC means I have to create something with an average value, right? So here what this equation is doing is just calculating the average value of this waveform at the output, right? So it's 1 over the period, which is 2 pi, integration of Vmax sine omega t, which is my input waveform, over the full period. But then this, of course, from 0 to pi, it has a value, pi to 2 pi, no value. So then you calculate the average value. So that's what this equation was doing. How about here? This is again like as soon as the diode started conducting, we went through the waveforms. The current waveforms look something like this, right? Initially, as soon as the voltage becomes positive, the diode will start to conduct. Input and output voltages are going to be equal, right? And then the diode will continue to conduct until the inductor current becomes 0, because it's going to try to flip after that. At that point, the diode blocks, right? So these are the waveforms that we went through. How do you come up with the equation of this current waveform? That's the objective, because we want to come up with this equation so that we can find out where beta is. Because when I find where beta is, then I can know if I'm trying to draw the output voltage or calculate its average value. Remember the average value, the output voltage here was input equal to the output all the way until the current became 0, right? So how do I know beta? I have to come up with the equation for current. So for me to come up with the equation for current, I go back to my 214 material, right? So this is a first order differential equation that is not 0. I don't remember what it's called mathematically. As long as it doesn't have 0 on one hand side, in the equality, then it has a natural and a forced solution. If this was 0, I will only have a natural response, right? But because I have a source, I have a forced response as well to the circuit. It's forcing a current into the circuit, right? So the solution to this differential equation is composed of a forced response and a natural response. The forced response is voltage divided by impedance. The voltage as a magnitude and an angle. The angle of the voltage is what? I think it's 0 in this case, right? Because it was Vmax sine omega t, so it starts at 0. And then the angle of the impedance, this is a magnitude of the impedance, and its angle is theta. And we brought it to the numerator by subtracting it from here, by subtracting it from the voltage angle here. Okay, so it's V divided by impedance, magnitude over magnitude, and then we subtracted the angles from each other. Right? When you have a magnitude, when you have two complex numbers, you divide the magnitudes and then you subtract the angles. Right? So that's exactly what we did here with the forced response. And to calculate, to calculate z as a magnitude, it's the square root of r squared plus omega l squared. Theta is inverse tan omega l over r. That's again.
So I can just do it in phase.
You can just do it what?
In phase.
Same. But we're trying to find the time domain equation.
Yeah.
Because we want to find, because beta is a value in the time domain, right? It's a value in the time domain, or which corresponds to a specific angle, right? So that's what we want to find there. So we want to find the time domain equation. So this is the forced response, right? The natural response is always going to be ae to the minus t over tau. The only difference is, at some points we can have a shift in axis, right? So instead of ae to the minus t over tau, it's going to be ae to the minus maybe t minus theta, for example, over tau. And we will see an example of that. But generally, since we're starting from 0, there's, this exponential starts at 0. So the solution will be ae to the minus t over tau. So the current is equal to this plus this. So we add them together, and we write the equation for current. It has a value of a. This a is an unknown, and we find it from initial conditions. What do we know about the current waveform? We know that at the beginning, I of 0 is 0. And we also know I of beta is 0. These are the two things that we know about the current. I of 0 is 0, and I of beta is 0. So we know these two things. So what can we do? I of 0 is equal to 0. We substitute with I of 0 into the current equation, and we solve for A. Right? So that's what we solve. This is when we solve for A. So after that, we can just take this A that we've solved for and plug into my time domain current equation. Right? So I plugged in and I found my equation for current in terms of time or in terms of radians. Right? It doesn't matter in terms of time or in terms of radians. It does not matter. All I have to do is just change the time here to radians as well, and the time constant to radians as well. So to angles. Right? So this is the equation for current. Now, what is my objective? I want to find beta. Right? I want to find where my current will become, it's called the extinction angle, the point where my current becomes zero. Right? So how do I find that? I know that I of beta is also zero. Right? So I can do the same, try the same trick. If I try the same trick, I substitute with I of beta is zero. I try to now solve for beta. This is a nonlinear equation that has no closed loop form. So you would do this on your calculator numerically. I mean, the TI calculators are all capable of solving an equation like this to find beta. Typically, that's what you would do. So please do that on your calculators and make sure you're able to do that. I mean, I know we've done it before on the calculator. I don't know how to do it on the calculator. I can do it on MathCAD or MATLAB myself, but your calculators, I am sure, that given all the rest of the other variables, you should be able to solve for beta. So any questions on this? So everything else you know, right? Everything, the voltage you will know, the impedance you will know, the angle of the impedance. I mean, you know the impedance is a magnitude and an angle. The only unknown here is you know the time constant, you know which frequency you're operating at. The only unknown will be beta. And you just cannot solve for it. You have to use numerical methods to do that. So this is the equation for current from 0 to beta. And the objective of this numerical solution was to find where beta was. So you know where you stop, which angle you're stopping at.
So it says there and equal L overall. That's that.
And equal?
Yeah.
Sorry, tau. This is tau, yes. And tau is equal to L over R. The time constant is equal to L over R. I think I wrote it up here properly. Did I? No, I didn't. Yeah, this is tau, the time constant. This should be tau. So any questions? So this is the equation that defines this current. And if you remember, all our circuits have the same shape of curve. So all of them will have the same equation, except the one with the source, we will just add a plus or minus VDC over R. We will just shift this to some extent. So this is the basic, this is it. This is the major equation that we have in the chapter. There's nothing more complicated. So for the capacitor filter, we will go through its equations as well. So anyway, so these are the waveforms we discussed last time. I will not go through them again. Unless you have questions, I will go. But besides that, I just wanted to skim through the equations, yeah. So here, again, we know that the waveform of the current will be very similar, right? And it's going to be a bit of a repetition here, but bear with me, right? So we write the voltage equation around the loop. So we go around the loop and write the voltage equation. We find that it's a what? First order differential equation with a forced response. Actually, this DC, you can bring it to the left because the DC and the AC sources constitute your forced response here. I have two forced responses, then I have my natural response, right? If I just bring the DC to the left, I have two forced responses in the circuit, and I have a natural response as well due to the first order differential equation. So how do you solve this? Again, you find the forced responses, which are two. In this case, it's the voltage over the impedance, which is demonstrated by this circuit here. And then it's the voltage over the resistance, because again, for a DC circuit, the inductor is a short circuit, right? In the case of DC, inductor is a short circuit. So if you're only going to look at the forced response due to the DC source, it's a steady state solution for the circuit. You will put you make the inductor a short circuit, and the forced response would be VDC over R. and the forced response due to the AC source would be the voltage over the impedance, like we did for the previous case. The voltage divided by the impedance as a magnitude, and then we subtract the angles from each other. Right? The angle was 0 for the voltage, and now I added a minus theta. Theta is the value of the impedance of the value of the angle of the impedance that's in the denominator. I bring it to the numerator in a negative by subtracting the angle. Right? So this is the forced response. Right? So same thing. I have a forced response, a natural response. Natural response is always AE to the minus T over tau, since it's a first order differential equation, Ri plus LdI by dt. And then the full current is the sum of the two, the forced response plus the natural response. When is this valid? From alpha to beta. Where is alpha? Before, in the previous case, alpha, the inception angle was 0. Right? The inception angle was 0, extinction angle was beta. Here it's the more general case. Inception angle is some alpha. Where is this alpha happening? When VDC is equal to my V input, my V max sine omega t. So when V max sine alpha is equal to VDC, I can calculate and find alpha, which is inverse sine VDC over VM. So I know where to start. But the same thing like previous case, I don't know where to stop. I know I will stop at beta, but this will end up being numerically resolved as well. It's the same. It's the same. I have an equation. I know where to start. I don't know where to stop. So here I will calculate A from the initial conditions because I know where alpha is. I of alpha is equal to 0. Right? From I of alpha is equal to 0, I will substitute I of alpha equal to 0. So this is I of alpha. It's equal to 0. I equate this to 0. Solve for A. So when you solve for A, I don't have it. I don't have it here, but you will solve for A, and then you will end up with an equation for current. This equation for current defines the shape of this current. This current equation is valid from where? From alpha to beta. Right? What do you know about beta? I of beta is also 0. So you do the same thing. You will end up with an equation like this. Here, the only difference is you will have a DC term that we added. But you will have an have an equation like this. The only difference is that you will have an additional DC term here, right? And this equation will still be something that you cannot solve. There's no closed solution for beta. You have to solve numerically with your calculator, right? So same, the process is exactly the same. So any questions on this? So alpha is no problem. We're okay with alpha.
And then we just check the function.
Yeah, you put I of alpha is equal to 0, solve for A. And that will be your equation for current. And then I of beta is equal to 0, you want to solve for beta. How do you solve for beta? Numerically.
Will it give you the same solution as alpha as alpha?
No, alpha is not. Alpha is where the DC voltage intersects the AC voltage. So this is defined value.
Well, in the function itself.
In the what?
In the function I currents doesn't have alpha as 0 as well because
Alpha is the solution.
alpha is the solution to the problem.
So alpha is another point. Yes, but remember numerical methods. Numerical methods you typically have to give a starting value. I mean, I don't know how you do it in calculator, but numerical methods generally numerical methods you have to assume a starting value. So if you get two values, you may get this value and then you may get this value. So you know that it's not the alpha. What else do you know about it? You know that it's going to be beyond which point? Where the resistor current would have stopped. Remember this is in this case it's the RL with the source. RL with the source. Where does the current for the resistor? If I have the resistor only, where would the current look like? The current will look like this, right? From here all the way until here, right? So you know that beta has to be greater than this point here. Where is this point? This point is also when VDC is equal to this waveform, right? So this can give you two values as well. This will give two values. This will give one value here, give one value here. So you know that beta will be bigger than this value. So all numerical stuff can give multiple values. So you have to know where you are around the curve here, right? So that's why I'm saying, like, go back. We will assign the homework today, so make sure you start working on it, and then solve these examples with your calculator so you can get used to something like that. Okay. I didn't go through the L source load because it's a very fictitious. It's not that doesn't happen in practice. Yeah. Then so I just skipped this one. There's nothing major. It's like just add a small r here and make the r smaller and smaller and smaller. If you do that, what happens? Huh? There's no exponential component. It's a 90-degree phase shift, and that's automatically 90-degree phase shift, right? So you integrate instead of having this the exponential equation. But it's fictitious, right? There's no such thing as a pure inductive load. So I just, for me, just if you understand the RL case and understand the consequence of, okay, increase R, how does the waveform change? Increase L, how does the waveform change? Increase the source, how does the waveform change? Decrease the source, how does the waveform change? Right? If you do that, like draw one case, and then you ask yourself, okay, if I increase the resistor, what will change on the waveform? If I decrease it, if I increase the inductor, if I decrease the source, if I increase the source, and draw all these waveforms, and if you feel comfortable with that and understand how to apply the equation, I'm happy. That's for me what you need to do. Okay. For the freewheeling diode case, again, same. Nothing changes about the current waveform. Why? There's no forced response, so it's the current waveform will be very similar to the initial, very first current waveform that we had for the half-wave rectifier with an RL load. So let's look at the equations. I don't think they even put the equations in. Oh, they do. But they put the equation. So for the case of, here they put the equation only for a very large value of L. For a low value of L, what does the current waveform look like? Here, let's look at this case. Remember, so this is my input voltage. For the current, what does the current look like? Without the freewheeling diode. Without the freewheeling diode, my current waveform looked like this. Correct? And my output voltage waveform looked like this, right? This is the input voltage, the output current, and output voltage. How about when I added the freewheeling diode? Input voltage doesn't change. How about the current? Current, load current, output current, I output. Is it going to change? It's going to be the same. I output will be the same. What will change will be the output voltage. Output voltage will look like input voltage all the way until here, right? And then 0. And then we said that at this point, this border here is the difference between the two circuits. So diode 1 is carrying this part of the current. Diode 1 is carrying this part of the current, and then diode 2 is carrying this part of the current. Right? That's the only difference between the freewheeling case and the case without the freewheeling diode. So is the equation for current going to change? Will the equation for output current change versus the initial case? It will not change. Right? So the equation for current did not change. So I don't think they put it even in the textbook. I didn't put it in the slides, but let me skim through the textbook. Yeah, they don't. Yeah, they don't do that. They don't have the details in there. It's the same. So how about the case where they put? It's a bit of a different case. We didn't cover this case. So here they said for a large value of L. So for a large value of L, what's going to happen? Let's look at the waveforms again. For the freewheeling diode case and a large value of L. So L is large. So L is small. Okay, let me draw the L is small case where we just did. This is the input voltage, right? And this is the output current, I output. And then this is the output voltage, plus minus the output, right? So how about for large values of L, what's going to happen?
Just to confirm, either it will always activate diode 2 or it will activate diode 1 when the positive is.
What do you mean it always activate diode 2?
Because then the current will always flow. Yeah, it's going to turn off, I guess, with the positive edge.
No. If I increase inductor, what is this going to do? Just if I increase inductance slightly, what will change in the waveforms?
It will always.
Which waveform will change? The red, yellow, or blue?
The current.
The current will change. Only the red waveform. What will it do?
Always.
It will move to the right. Keep moving to the right. Okay. At some point, what happens here? At this point, your diode 1 starts to conduct again. Diode 1 starts to conduct, then I'm starting to build up current again. I'm starting to put positive voltage across my inductor. I was putting positive voltage. What inductor voltage? Remember, inductor voltage is equal to what? Equal to the VL is equal to the supply voltage minus the resistor voltage. Right? The resistor voltage looks like the current. So resistor voltage is 0 when the current is 0. Supply voltage is positive, so I'm putting positive voltage across my inductor, so current is rising in the inductor. Right? At some point, what happens? At some point, the resistor voltage becomes high, supply voltage becomes low. Remember, this is multiplied by the R value, then this will go up. This will be scaled. To find VR, this will just be a scaled version. This is VR. Right? And then you subtract V input minus VR. At some point, they're equal. Beyond that point, what happens? VR is greater than the supply voltage. So this becomes negative. As soon as it becomes negative, the inductor current starts falling down. Right? That's what happened here. Now we said that I increase the value of inductor. If I increase the value of inductor, I will push this further and further to the right. At some point here, I'm creating, again, Vs minus Vr will be not at this point, but maybe beyond it. Like let's keep pushing this thing to the right. Let's keep pushing this thing to the right, and maybe here, or no. Let's keep pushing this like this. For example, if I keep pushing it, this is another value for another shape the current can take, another shape the current can take, another shape the current can take. Remember, VR is a replica of this but scaled. So I can draw VR now instead of like this. I draw it. I'll just draw it for this last case. Okay. Scaled version of this is VR prime. Right? And then what's happening? At some point, Vs minus Vr are 0, same. And then what's happening here? Vs is greater than Vr, right? Vs becomes greater than Vr. If Vs becomes greater than Vr, I'm going to start pushing current up again. Right? I'm going to apply a positive voltage across it, so push it back up again. So then this will, if this is the critical point where, for example, at this point they're equal to each other, so the Vs is equal to Vr, so inductor voltage is 0, then the current becomes 0, for example, right? But then, as soon as I get to here, one point beyond that, the current will rise again, right?
The voltage will spike like that at this point.
Which voltage will spike?
The voltage, the out.
V out. No, you tell me. Assuming now, let's say this now I push it a little bit further. I push it a little bit. If I keep pushing it further and further, I make it. I move this point where the current becomes, this critical point. Maybe I didn't draw to scale properly. Okay, so this VR I should have, again I should have drawn it a little bit on the same slope as the current. Yeah, but basically at some point this current does not fall down anymore. Beyond the point where the voltage starts becoming positive. Here the voltage Vs starts becoming positive, and VR is doing what? Decreasing, right? At some point, beyond this point, beyond here, this voltage minus VR becomes a positive number, and current starts to rise again. So it will look like this. It will look like this. At some point, it will not fall down all the way to 0, right? It will there is a critical point where it will fall down to 0, of course. But if I draw to scale, I can draw it nicely. But at some point, this beyond here, it has to be beyond here, because beyond here is when Vs starts to become a positive number, and VR was decreasing. Where exactly is this flip point? You have to draw to scale. I have to draw the waveforms to scale. But there is a point beyond this here, where if you keep increasing inductor, the value of the inductance, Vs minus VR becomes positive, and the current will start rising again. Right? So the current will start rising again. And that's the case that they discussed here in the text. So, if it starts rising again, that means it will continue to oscillate like that. So they draw it here a little bit nicer, easier to understand. So here. But the voltage, of course, doesn't change. Right? The voltage does not change. The output voltage is still 0 all the way until here.
And then after the
When it becomes positive again, not after the breaking point, exactly at 0. The voltage becomes positive. Right, because the voltage again, if the voltage was negative all the way here, right? The current has an easier path to flow. It has an easier path to flow. Now the voltage becomes positive here. The easiest thing to do is to turn on this diode.
the resistance has more voltage to resist the non-diode one, doesn't it?
The resistor has some voltage
More voltage than the
on it,
Vs.
but the inductor voltage is negative. Remember, we're in the falling. It's falling, so inductor voltage is negative. Inductor voltage is negative. Inductor voltage is negative. VR is a small positive value. There will be a small opposition to diode 1 turning on. Yeah, right. Inductor volt. This is negative. This is a small positive number, so this is helping diode 1 turn on. Right? So it's as soon as the diode 1 has a opportunity to turn on, it will turn on. Okay, so what happens here is that the voltage will still be like the case we discussed for the RL load case with a small inductor here, right? But the current will be continuous, right? So what were we doing before in the previous cases? Trying to find the equation for current. Right? For the previous circuits, all we did was try to find the equation for current. Why did we want to find the equation for current? So we can draw it properly. Right? And then if I draw it properly, it means I can calculate RMS. If I have the equation, I can calculate RMS value. If I have RMS value, I can calculate power. If I have, all of that, I can do everything I want. Yeah. So now the objective is the same. I have this current waveform, this output voltage, and this current waveform. Right? If I have this current waveform, how can I calculate the equation for this current? Remember, our objective is to be able to calculate powers, for example, right? So I need RMS voltage, RMS current. So for my voltage waveform, it's a periodic waveform, sinusoidal for half the wave. So I can go to my Fourier series sheet and use the equation, use the Fourier series for the half wave rectified sine wave that we have on there, right? How about for the current? Is this current half wave rectified? No. Is it the same as the RL circuit current that we found before? We found the current for before? No. It's a continuous current. It never falls to zero. So I don't have alpha and beta or zero and beta, right? So how do I find the current in this case? The way it's proposed to do it in this case is to apply Fourier series. So if I know my voltage equation and I know my load, then if I divide by the voltage by the impedance, I can find current, right? So that's what they would do. But you would have to do that for each harmonic, right? Because it's a linear load. Remember, a linear load, you give it first harmonic, it will give you a first harmonic. Give it second harmonic, give you a second harmonic, and so on and so forth. So that's exactly what they did here. The underlying assumption is that if I find each voltage harmonic and divide it by the impedance at that frequency, then I can get the current at that harmonic, at that frequency. So I know that impedance is R plus J N omega L. So depending on the frequency, I multiply by the specific harmonic. So I go to my Fourier series data sheet, Fourier series equation sheet for the half wave rectified sine wave, right? And what do I get? I get that the output voltage in Fourier series equal to V max over pi. This is its average value. First harmonic, second, fourth, sixth, etc. So on. This is the Fourier series for this half wave rectified sine wave. This is something you don't need to memorize. It's in the sheet that I gave you for Fourier series. Then how do you proceed from there? You take each of these harmonics and divide it by the impedance at that harmonic, right? So if I want to find the average value of current, it's the voltage, average value of voltage divided by the resistance. If I want to find the first harmonic of current, I take this value of voltage divided by the impedance at the first harmonic, and so on and so forth. So they do that in the next sheet. So before we go there, similar to what we did, diode 1. These are the currents in diode 1 and diode 2. So they've drawn those for you. This is diode 1, this is diode 2. Remember, so diode 1 is conducting here all the way until here, right? All the way until the voltage becomes 0. As soon as the voltage becomes negative, the current finds it easier to push the current through diode 2, right? So diode 2 carries the current in this part of the curve. Right? As soon as the voltage becomes positive, diode 1 finds it easier to conduct. And diode 1 conducts again in this portion of the curve. Right? So this is diode 1 current and this is diode 2 current. Okay? So, if we... Which one? This? It's not a straight line, it's exponential, right? Should be an exponential because you have the freewheeling diode and the RL circuit, so it's an exponential. Right? Here it's not an exponential. Here I have a forced response and an exponential together, right? And so it looks like a rising exponential waveform, but it's not really exponential in here. This is not exponential. This is exponential, pure exponential without a forced response. Okay, so now we have this Fourier series. So what do we do to find current? Again, I don't think they put it here. They don't even calculate it, but there's a good example on it. I did not solve the example. I'm sure you will have a homework problem or something that looks like it. But if you take your textbook, example 3.7. Example 3.7, they do exactly that. They take this equation and find each corresponding harmonic. So they take the average value divided by the resistance. They take the fundamental divided by the value of the impedance at the fundamental frequency. Third harmonic or second harmonic, voltage divided by the impedance at the second harmonic. So that's example 3.7 in your textbook here. So I will not do it here since there's a good example about example 3.7 in text. They go ahead and calculate every current harmonic, and then they create a table, a nice table. You know, the fundamental, the harmonic, the harmonic number, the harmonic voltage at that harmonic, the harmonic value of the impedance, and the harmonic value of current. So they go through that. They do the calculations for you extensively. But that's the objective. The objective is to always find voltage and current equation. So I can calculate my power, I can calculate my THD, I can calculate the power factor, I can calculate whatever I want. And because we are not able to come up with an equation for a closed form equation for current here, I have to resort to Fourier series. Okay, so that's the objective, the story behind this. Here, this is the case of, okay, if I make L over R infinitely large. Of course, this is a fictitious case, but it's good. I mean, these fictitious cases are nice to draw waveforms. So if you want to understand, okay, when is diode 1 going to conduct, when is diode 2 going to conduct, again, in this fictitious case, you just have straight lines. You know, L over R being infinite means this current does not change, right? These currents are fixed. Okay, L over R being infinite, yeah, right? So I have an infinitely large L. So if that's the case, then current will never change. It will be, it's like, remember the case where I said that we have a current source at the output last time? I said we can model this as just as a current source. So instead of drawing this RL, we just have a current source here. So this is the case where L over R is infinite. And if this is a current source, I always have to provide this current. If the voltage is positive, I provide it through this diode. If the voltage is negative, the freewheeling diode picks up. Right? Yes? No? I don't know, you seem too quiet today. Huh? Too many equations? So maybe we should finish the equations and have a quick quiz, huh? It's easy, it's good, it's good. So we'll have a quiz on the waveforms right after. So we finish this and we'll have a short quiz on all the waveforms. Just to lighten things up, you know. Anyway, so for capacitor filters. So what did we say is happening here? Okay, actually what did we say is the objective of this circuit here? What was the objective of this circuit? All of them were create AC, DC from AC, right? But remember, we said we had a DC, or a waveform with an average value, but with a huge ripple, right? Remember, initially we have what? A half-wave rectifier. Without this capacitor, the output voltage looked like this, right? This is my output voltage. My circuit, my load, does not like something with a huge ripple, or delta V is basically the difference between the highest voltage that the load sees and the lowest voltage the load sees. So it sees, you know, this is my waveform, so it sees 0 and it sees V max, right? This was my delta V, this is my ripple. This is a huge amount of ripple, right? You know, typically you will have a spec on ripple, and this spec can be 10%, 5%, 1% of your typical rated voltage of the device. So let's say this device is rated for 10 volts. Your cell phone chargers are rated for 3.7 volts, for example. Then the power supply that you are requiring to charge this cell phone, for example, may be something that will accept 3.7 volts plus minus 10%. So it's 10% of the 3.7 volts is your delta V. So half of it is on top of 3.7. Let's say this is your 3.7 ideal value. 3.7 is your ideal value. So you're accepting a delta V of 10%. So this is delta V equals 0.1 times 3.7. That is your ripple. That's what you will accept. You will have a ripple spec. Every power supply will have a ripple spec. It's part of what you have to do to build a power supply. You cannot just say, I want a 5-volt power supply, because somebody can give you something with an average value of 5 volts. That is nothing but this. It's a half-wave rectifier that has an average value of 5 volts. But this is not going to be something to power up your load. So you have to specify a ripple. So we added this capacitor to filter our waveform. So this is my waveform. It's a periodic waveform, non-sinusoidal. It means it has AC components or harmonics as well as an average value. I want something that looks like the average value, closer to the average value. So I want to basically filter some of the AC components. That's exactly what I want to do. So you can do that by adding this capacitor. Later we will see that, or right now we will explain why sometimes we don't just use a capacitor by itself. Sometimes we use an inductive filter with a capacitor as well. So we will see that. We will see that shortly. So this was the objective: is to filter the output. So now my output is looking something like this, which is a waveform. We went through the waveform before. So now my ripple is this much. This is my new delta V after I added the capacitor. Right? A lot less than before. How do I decrease this even further? We need to come up with an equation by increasing the capacitance. Fine, we understand that from the logic of what I explained, but we have to make sure we have, how much increase? We have to find an equation. So this will be the equation that we will do. But I will go through these equations to see how we came up to here. But let's look at this equation. The equation for is delta V is equal to Vmax over F RC. Right? So if I increase the capacitance, definitely my ripple will decrease. What else did we say as well? What else does this equation say? If I increase my resistance for the same everything else, then also my ripple will decrease. Makes sense or not? Remember how we said that this, what's happening here is that the capacitor is starting to discharge. Where is it discharging? It's discharging to the resistor. If I increase the value of resistor, what happens? I'm taking less current out of the capacitor, which means that my capacitor voltage will change less. Right? If I'm taking less current out of it, then the capacitor current will change, capacitor voltage will change less. Right? Because the current out of the capacitor can only go through the resistor. Cannot go back to the supply, because the diode will block. It will go through the resistor. If this resistor is large, meaning the current is small, then the value of voltage across the capacitor will not change much. If I'm not taking much current out of it, then its value of voltage will not change. Right? That capacitor voltage changes by drawing current out of it or removing charge from the capacitor plates. That's exactly what's happening here. So that's one other thing. What's another? So now we see C and we see R. How about F? If I increase frequency, this means that if I increase frequency, I decrease ripple automatically. Why is that? This is a bit... Exactly. Right? So they will be closer. So for the same value of R and C, right? Remember, what's happening as soon as the diode disconnects, right? Then this capacitor is discharging to the resistor, right? If I make the charging occur more frequently, the discharging, does this charging slope change? Does the slope of discharge change? Where did we get this slope from? This is an exponential, right? Where did we come up with this equation for this exponential? From the RC circuit, right? So the RC is the same. If I don't change the R and the C, right? But I make these half waves closer to each other. What happens? In that case, I will discharge less because let's say I have, now I bring this blue waveform to the left and I have, something that is here, right? So instead of discharging all the way to this point, I will discharge to this point. So automatically I have lower delta V that way. That's why in power electronics, why do people want to use silicon carbide and gallium nitride, and why? It's because they can operate at higher frequencies. You operate at higher frequencies, then you have the advantage of being able to use smaller capacitors and inductors. That's one of the big advantages of the silicon carbide gallium nitride revolution, if you want to say, in power electronics. Yeah, right. It's because we can increase switching frequency. Of course, the other thing is these devices are lower losses. So, but it makes sense because you're switching a lot faster. When you switch a lot faster, you're more prone to switching losses, right? If you're switching a lot faster, that means, and if you have high switching losses, then you cannot tolerate. Then the temperature will go high, and you will burn your device. But these devices have a big advantage is that you can switch them very fast, which will allow you to use smaller L's and smaller C's, and they will survive at that temperature. So their switching losses are very low, and they can actually survive at higher temperatures as well. So they have lots of benefits from a device physics perspective. Right? So here we understand where this equation comes from. At least, we understand the parameters of this equation. Right? So now let's see where it comes from. So initially we said that we have, when the diode is on, the input voltage is equal to the output voltage, right? So this is output voltage, and my input voltage is Vmax sine omega t, right? So initially, when the diode is on, my voltage is at the output is equal to the voltage at the input is equal to Vmax sine omega t, right? At some point, when the diode turns off, and we discussed when the diode turns off, right? So as soon as the capacitor starts to discharge, right, it has not able to discharge through the source. It will discharge to the resistor. Fine. This will, discharge a little bit of current, from the capacitor to the resistor, but at some point, the supply current falls. The supply current is falling. Because the supply current is falling and the capacitor is in parallel, that means you do have to do what? That the capacitor. Assume you just have a supply and a capacitor. If the supply is in parallel with the capacitor and the supply voltage is following, what does this capacitor need to do? It needs to discharge to the supply. If there's no resistor connected, right? It's going to discharge to the supply. As soon as it tries to do that, the diode blocks. Right? If the diode blocks or the diode becomes off, then I'm left with my RC circuit. Right? And this RC circuit, the voltage across this, the current through this RC circuit, or the voltage across the resistor, is an exponential, AE to the minus T over tau. Right? AE to the minus T over tau. A happens to be the value of voltage at this point V theta. Right? And then E to the minus T over tau, we have a change in axis. So instead of instead of minus T over tau, it's minus T minus a shift in axis, T minus theta, right? So AE to the minus T over tau, T minus theta over tau. And then, here they drew it in terms of angles, not time. So we drew it in terms of angles, omega t. So I just changed this to an omega t instead of t. So omega t minus theta. Right? So the equation for the exponential is AE to the minus t over tau. It's an exponential function. This exponential function, where does it start? It starts at theta. We don't know where theta is yet. We don't know where. We said that there's a point theta where what happens? Where the input voltage is falling a lot faster than the capacitor's voltage. The capacitor is discharging. So if that's the case, then the diode will turn off. If this input voltage is falling fast, and the capacitor voltage cannot follow. Capacitor voltage cannot follow. At some point, since that's the case, then the capacitor voltage becomes higher than the supply voltage, and the diode blocks. Right? At that point is called theta. This point here is called theta. This point where they start diverging is called theta. We don't know what its value is. We have to calculate its value. Right? We will see how to calculate its value. Like before, we were calculating alpha and beta for the current. Here we have to calculate theta, because that's the point where these two waveforms start diverging. And then we also have to calculate this point, because if I know this point and I know my maximum value, then what do I know? The ripple, exactly. And if I now have an equation for ripple, which is the difference between these 2 points, and this equation is in terms of the R's and C's and the frequencies, etc., etc., then that's what I want. I want to design ripple. I want to design my converter to maintain a certain ripple voltage here. So that's the objective. So here, These are the two equations when the diode is on, when the diode is off. Then at some point theta, at omega t is equal to theta, these two curves start diverging. So their slopes will start becoming different. Right? When the two waveforms start diverging, that means their slopes become different. So I will find the slope of this one, find the slope of this one, equate them to each other, and at that point, this is the point. If I solve this for that angle where they start diverging, then I will have this value of theta here. So this is Vmax sine theta. What is the slope of that? It's a differentiation, right? Slope is the differentiation, right? So Vmax sine is cosine, right? At Vmax sine theta or Vmax sine omega t, where I want the slope at point theta, right? So I will, this is Vmax sine theta, and I differentiate to find the slope at point theta, which I'm looking for. So I have Vmax cosine theta on one side. And then I find the slope of this as well. I also want to find, excuse me? I want to find the slope of this other equation also at this point theta, right? So omega t I will substitute with theta, right? So I also substitute with this omega t with theta. And yeah. So I substitute omega t with theta. That's what they did here, right? That's what they have here. So I do this. I find the slope of this side with respect to at theta, and and then I equate them to each other. So I want to find the slope of the input waveform, and then find the slope of the exponential, so the slope of the input waveform, and the slope of the exponential at this point theta. I equate them to each other, and that's what I have here. And then this is an equation in terms of what? Omega, R, C, Vmax, and theta. I solve this equation for theta, and I have this equation for theta. So theta is equal to inverse tan omega RC plus pi. Right? So this is a closed form equation for theta. What else do I need? I need to find theta, and I need to find, my objective is delta V. So for me to find delta V, I need to know where this point is. This is the point alpha, which is at this point here, or 2 pi plus alpha away from the starting point. Right? So I want to find this point. How do I find this point? This point is the intersection between the exponential and my input sine wave, 2 pi plus alpha after the zero crossing. I don't know if it makes sense or not. So my input sine wave is Vmax sine omega t, or sine theta, right? Vmax sine 2 pi plus alpha is where? Vmax sine 2 pi plus alpha is this point here, right? This is Vmax sine omega t, all the way until 2 pi plus alpha, right? So if I equate Vmax sine 2 pi plus alpha, if I equate it with my equation for the exponential, then I have an equation that includes what? It includes alpha and theta and omega and r and c, etc. All of my parameters. So here I equated my input sine wave with my exponential at a point 2 pi plus alpha.
What is alpha?
Alpha is the point where these two waveforms intersect. Why is it important? It's important because it's the lowest.
They intersect at alpha?
Huh?
They intersect at alpha?
Yeah, they intersect at alpha. So this intersection is alpha be after this is 2 pi, and this is an angle alpha. Maybe I should clean this. This is 2 pi here, and this is an angle alpha after 2 pi. So they intersect at the angle 2 pi plus alpha here. So you have your equation for the exponential, and you have the equation for your input sine wave. You calculate the value of the input sine wave at 2 pi plus alpha. you calculate the value of your exponential at 2 pi plus alpha. Equate them with each other, right? And then you will have an equation that you know everything about except alpha, right? Because theta we know from here. R and C we know because they're your circuit components. So the only thing you will have left in this equation is alpha. Or if you're designing your circuit, then this is a way to include all the variables at one point in the same equation. I don't know if it makes sense or not.
So we're solving for alpha here?
I have to solve for alpha. You have an equation that you want to solve for alpha. Same as the beta before. It cannot be solved. There's no closed form solution. You cannot just take alpha out because it's inside the sign, etc. So you have to solve this numerically for alpha. Okay?
So where's the ripple voltage in the equation?
The ripple voltage is Vmax.
The difference.
Yeah, it's Vmax minus V at alpha. So how do you find V at alpha? You have to find alpha and then just substitute in your equation. Vmax sine theta.
You're given Vmax.
Yeah, you're given Vmax, and you know that this is just nothing but a sine wave.
Yeah.
But where do you stop? You stop at alpha. This value of alpha you don't know, so you have to find an equation to help you calculate alpha. So you do that by intersecting the exponential with this, and they're both in terms of alpha. This is in terms of alpha, the exponential in terms of alpha, and the sine wave in terms of alpha. So you know that they are equal to each other at this one point alpha. So you equate them to each other and calculate alpha. Can I calculate alpha closed form solution? No, I cannot. I have to use numerical methods, meaning you have to use your calculator to do that, right? So that's the process, right? And then what is delta V? So now if I have alpha and I have theta and everything, then finished. That means I have this point, and I know my maximum value. So my delta V is Vmax minus the voltage at alpha. That's my delta V, right? So it's Vmax minus Vmax sine alpha. That is your delta V, right? So calculating alpha is a pain, because of the numerical solution, etc., etc. So in the case where you are trying to, so then you can go through, the textbook goes through and shows that I can go from an equation like this to something much more simplified. Instead of solving this numerically and then substituting this equation, you can do that. There's nothing wrong with that. This is the right process. But if the textbook goes through an expansion, they expand this using a Taylor series, and they do some mathematical manipulation, and then they say that for V theta close enough to Vmax, and for theta close enough to pi over 2, which is the case that we want to design for, right? Remember, we said that typically we want to design for low ripple. Low ripple means what? Means that the current in the resistor is not very high. If the current in the resistor is not very high, what's happening? This is your input. If the resistor current is not too high, then your capacitor will charge to a value of Vmax, and then fine, it will discharge. But the discharge will not be much, right? So let's say I will be here. Then I continue again. So this is now your ripple, right? So if the ripple is small, they're saying that when they go through the mathematical manipulation of that equation, in the case where the ripple is small, which is typically what you're trying to do, you're always trying to make 5%, 2%, 3% ripple. If you do that, then which means that remember V theta was the point where the two slopes became different. Where is V theta here? Very close to Vmax, right? Where is theta? Theta is very close to pi over 2, right? When theta is close to pi over 2, which means that Vmax is close to, Vmax and V theta are almost the same, which is typically what you're trying to do when you're designing a capacitive output rectifier trying to create DC, right? That's the case. Otherwise, you're doing what? If this is not the case, and you have V theta all the way here, what does this mean? It means that your waveform looks like this. right? This is your output voltage, this, then 0, then you have this, and it goes down to 0. This is now, doesn't make sense. This is huge delta V, it's the same delta V as before, right? So this is not the case that we're talking about, right? Here, V theta is not equal to V max. And theta here is not equal to pi over 2, right? This is a case where you don't want to design something like that. You want to design something that looks like this and like that. If you are doing this, you don't have to go through this hassle. You don't have to go through any of this hassle. You just use this equation. This equation is after they take this equation and do some simplifications and try to do the subtraction, you get a relationship between the ripple voltage and the circuit component that is very nice and easy to just substitute in. So I will not ask you to derive it, but in the homework you will have cases where they tell you that the time constant is very large. The RC time constant is large. And some cases where they tell you the RC time constant is small. If the RC time constant is small, that means you're discharging quickly. If the circuit time constant is large, that means that you're not discharging quickly, and you have this case where you can use this equation. So in the homework you will have both. You will have cases when you will use this equation right away, and you will have the case where you have to calculate alpha, theta, then alpha, and then calculate the delta ripple. Right? So you see where you can use this and where you cannot? Right?
That's only if it's small.
Yeah, if the ripple is small, you can use this equation. The ripple is large, or the time constant of the circuit is such that you are discharging very fast. They will be clear in the homework. They tell you you're discharging at twice the rate of your input sign, or something like that. Right? They will be very clear. It will be clear where something is something where the ripple is small versus something where the ripple is large. Something where the ripple is large, you cannot use this. You have to use this, the regular equations. Calculate theta, calculate alpha, do the subtraction. We clear on this? Yeah. That's load dependent. I mean, that's your customer. That's your customer needs. You're in a senior project, customer needs. That's part of your customer needs. Okay. So the other thing about these filters, you remember, we said that as soon as the capacitor, the input voltage becomes greater than the capacitor voltage, what will happen? The diode starts conducting again. When the diode starts conducting again, I have to charge my capacitor, right? And I'm going to charge my capacitor. The voltage on the capacitor is now going to change from a negative slope. Remember, this is the output. V output is the voltage across the capacitor. It has a negative slope here. And now it's going to be converted to a positive slope. So we said that the current will be very high. So, and we saw that this current is going to be very high. Where is this current going to come from? My supply. So does the supply like to provide peak pulses in current and then zero? Pulses in current, zero? No, the supply likes to provide a nice RMS value with a low value, so that it doesn't have to rate its components for higher currents. So this is in the case where you only have a C capacitive filter, this is always the case. And capacitors always do this to the current waveform. They make it very spiky. So we will see later in another chapter that sometimes we add an inductor here. What does this inductor do? In this case, the inductor will smooth out the current. So because there's an inductor, can current rise abruptly? No, current will rise slowly. So fine, you still have very similar performance, but the current will rise slowly and will fall slowly. There will be no abrupt changes in current anymore. So, and what will that do? That will decrease the maximum current rating of the diode. So that's good for your power electronics as well, right? So we will see that in another chapter. In what? No, not in parallel. I'm serious. Because if it's in parallel, then it will not really affect the diode current. It will change the impedance, right? Because now you have inductor in series with a capacitor and parallel with the resistance versus inductor in series with a parallel combination of an R and C. Here, this will not maintain, if you have an inductor in series, you will not be able to maintain a certain specific output voltage. Because I don't know, I have to look at the equations here. But the output voltage, capacitors maintain voltage. Right? Maintain a specific average value for voltage. Inductors, they maintain average voltage of 0. So we would have to look at the equations here. So unfortunately, time is up, right? But I'm not going to continue this. So this, what we see here for the equation for current. Here, what did we do with the thyristor? Sorry, just quickly. For the thyristor, the only thing that happened was I added an alpha, and we said that this decreased the average output voltage. So calculation of the average output voltage, instead of being 1 over the period, integration over the period, it's 1 over the period, which is 2 pi, integration from alpha, which is the firing angle of the thyristor, all the way to pi, because I know that the voltage becomes 0 after that. Yeah. So here's calculation of the output voltage. You need to note that. RMS value, calculate that. I mean, there's nothing really amazing here. Here we added the L. When we added the L, we saw what happens to the waveform. And again, what do you note about the current equation? And exactly the same. It's the same equation. It's voltage over the impedance plus AE to the minus T over tau, because the current shape is the same, right? So this is valid from alpha to beta. How do you find A? A is from initial conditions. Initial condition is I of alpha is equal to 0. So I of alpha is equal to 0, you'll find A. And then how do you find B? Beta. I of beta is equal to 0, and then it's still closed form solution you cannot find, so you have to do it numerically. Exactly like before, yeah. Yeah, it's one single equation for the whole chapter. It's honestly the same equation for the whole chapter. The only difference is sometimes it will have a DC force response, sometimes it will have a DC and AC force response. Okay, sometimes it has AC only, and sometimes it has DC and AC force in the force response. But really it's exactly the same. So and we went through commutation quickly last time, and we said that the effect of commutation is what? That the output voltage becomes 0 for a piece of time, for a period of time. Again, the equation for that is, I will stop here, I don't want to. So the effect is the reduction in output voltage. So instead of calculating the average value from 0 to pi, we calculate the average value from U to pi. Next time I'll just talk about this U, and then we go to the next chapter.
Sir, did you mention anything about